Here we go. In lecture today, we discussed what happens if you look at the moments about a point P, which occur due to forces at a particle I. We sum those for the entire body, which has pretty much infinitely many little particles I, only a few of which are going to have external forces at them. Anyway, the result we got was this equation right here, which is Hibbeler equation 17.6. And what it says is the sum of the moments about any point P is going to be moment of inertia about that point, IP times alpha, minus y bar m apx plus x bar m apy, where x bar and y bar are the distances from P to the center of gravity in the x and y directions. AP is the acceleration of point P, and m is the mass of the body. And what we want to do, if we scroll down to page 9, we want to look at what happens if point P is not fixed, and if it's not the center of gravity. Suppose we want to get that previous equation, which we'll rewrite here. Sum of the moments about P, positive counterclockwise, equals minus y bar m times P's acceleration in the x direction, plus x bar m AP in the y direction, plus IP alpha. So again, that's equation 17.6. Okay, suppose we wanted to rewrite this in terms of IG, the moment about the center of gravity, which is the one that you normally see tabulated in the back of your book. Well, we could use the parallel axis theorem, which says IP is IG plus MD squared. What D? Well, the distance from a z-axis through P to a z-axis through G. That distance is the magnitude of this r bar position vector. That distance is also, using Pythagoras, the root of x bar squared plus y bar squared. Okay, so IP is IG plus M times the magnitude of r bar squared, which is going to be IG plus M x bar squared plus y bar squared. All right, so if we substitute that into equation 17.6, we have sum of the moments about P equals. Now we had a y bar m AP in the x direction. We're going to get an mx bar squared alpha. We're going to get an my bar squared alpha, which is basically my bar times y bar alpha. Okay, so that's the my bar squared alpha from the parallel axis theorem. We had originally an x bar m AP in the y direction. The parallel axis theorem is going to give us an mx bar times x bar alpha. And there's the IG alpha from the parallel axis theorem. So if we look at the first two terms, we've got y bar m outside of minus apx plus y bar alpha. We also see that we have x bar m in the third and the fourth terms. So we can finally rewrite this as sum of the moments in the P direction, or sum of the moments about P is y bar m outside of minus apx plus y bar alpha plus x bar m outside of apy plus x bar alpha plus IG alpha. Now that equation in the Hibbeler text is equation 17.8. What we're going to do now on the next page is we're going to write, instead of writing the acceleration of P, let's put this in terms of the acceleration of G. So we're going to take our original moment equation about P. We're getting rid of IP in favor of IG. We're getting rid of the acceleration of P in favor of the acceleration of the center of gravity. Because when we apply Newton's laws in the x and y direction, we're going to be working with m times acceleration of g. So we're going to write ag is equal to ap plus acceleration of g with respect to p. All right, so we'll do that on the next page. Okay, if we come down to the top of page 10, well, acceleration of g, that's agx in the I direction plus agy in the j direction, and that's going to equal acceleration of p. Okay, acceleration of p is going to be apx in the I direction plus apy in the j direction. Now the acceleration of g with respect to p, that's going to have a tangential component and it's going to have a normal component. Now the tangential component is going to be alpha cross r bar. So alpha is alpha k, and we're going to cross that with the r bar vector. So if we look up here, if this body has angular acceleration alpha that way, then here's the direction of acceleration of g with respect to p tangential, and that vector is going to be alpha k crossed with r bar, which is x bar I plus y bar j. Alright, so we'll get rid of that. We know it's there. Okay, AG equals AP plus g with respect to p tangential, alpha k crossed with x bar I plus y bar j. The normal component is minus omega squared r. So we can write minus omega squared times that r bar vector. Now, if we work out these cross products, when we do alpha k crossed with yj, for example, we're going to get a minus y bar a in the I direction. So if we look at all the I components in this equation, acceleration of gx on the left-hand side is going to be acceleration of px minus y bar alpha. And if we work through the other cross products, we'll see a minus x bar omega squared. And that gives us minus acceleration of px plus y bar alpha is equal to minus agx. Running out of room here. Let's move all this stuff over a little bit. So I'm just rearranging that equation, which is all the I components. So we'll see if we can move that over. Move. There we go. Okay, so back up to my pen. Give me the pen. Thank you. Alright, so I get minus apx plus y bar alpha equals minus agx minus x bar omega squared. Any day now. There we go. Okay, get rid of those guys. All right. If I gather all the j components from the previous cross products, I'll get acceleration of g in the y direction will be equal to AP in the y direction. I'll get a plus x bar alpha, and I'll get a minus y bar omega squared. So that gives me the following equivalence. APY plus x bar alpha is going to be AGY plus y bar omega squared. Now, what good is that? Well, if we take a look at minus apx plus y bar alpha, if we go up to the previous page, in our equation 17.8, you can see that we have minus apx plus y bar alpha. So we can get rid of that, and we can substitute the expression we just got. So this allows us to rewrite equation 17.8 as follows. Sum of the moments about P equals y bar m outside of minus agx minus x bar omega squared plus x bar m outside of agy plus y bar omega squared plus ig alpha. Now let's see, we've got a y bar, we got a minus m x bar y bar omega squared. Here we've got a plus m x bar y bar omega squared, so those terms will cancel. And this simplifies down to the following. Sum of the moments about P equals ig alpha minus y bar m agx plus x bar m agy. Now that in Hibbler's text is equation 17.9. So I want you to take a look at that for a second. What I want to do down here below on page 10, I want to rewrite that. So I want to write 17.9. I want to bring a couple of terms over to the left-hand side. Some of the moments about P. Now these are all the externally applied moments like M1 and M2. They're also the moments due to applied forces. F1 times the perpendicular distance, F2 times the perpendicular distance. The sum of the moments about P plus M agx y bar minus M agy x bar equals ig alpha. So the sum of the moments about P doesn't equal just ig alpha. Okay, the sum of the moments about P plus these two extra terms that kind of appear to be moments. Okay, the sum of the moments about P plus these two extra dudes, that equals ig alpha. How can we account for these moments? In the past, I've spoken about inertial force. So if this body has a center of gravity g, and if its acceleration is positive, okay, so if ag in the x direction is to the right, and if agy is upward, the inertial force, I've said, is equal to minus ma, but opposite the acceleration. So that would give me an inertial force. Here's an inertial force mag in the y direction. It's opposite agy. Here is another inertial force. Here is inertial force m times ag in the x direction, opposite the x component of the acceleration. What are the moments about P due to the inertial forces? Well, I have a counterclockwise moment, magx times y bar. I have a clockwise moment, which is negative, magy x bar. So those two extra terms in my equation for the moments about P, the magx y bar and the minus MAGY X bar, those are moments about P due to the inertial forces. Moments about P due to inertial forces. So again, inertial forces, we never draw those on the free body diagrams when we're using Newton's law for F equals ma. But if we want to take moments about a point P that's not the center of gravity, or a point P that's moving, we can take moments about P as long as we include the moments about P due to the inertial forces. And then all that stuff equals Ig alpha. So on the next page, I'm bringing this up not because you're ever going to need to sum moments about an arbitrary point P. You're always going to be able to get away with taking moments about the center of gravity or sometimes a fixed point. But when you look at Hibbler's solutions, which you will because the solution manual is online, and that's why I can't give you problems out of Hibbler anymore for the assignments, his solutions often use the sum of the moments about an arbitrary point if that's convenient. Plus, you've shelled out a lot of money for the textbook. You're probably going to read it, and I don't want you to be confused when you see that particular approach to problems. So I say sum of the moments about P, including the moments due to the inertial forces, all that equals Ig alpha. What Hibbler does is he says sum of the moments about P, computed in the usual way, moments from, okay, so these are moments from external forces or applied moments. Hibbler says sum of the moments about P equals Ig alpha plus the y bar m agx and the x bar m agy terms just brought over to the right hand side of the equation. He calls all three of those together kinetic moments. That's his term, I think. I haven't seen it in any other book, and he gives it a symbol stylized m sub k about P. So in his solutions, you'll see sum of the moments about P equals sum of the kinetic moments about P. And the reason I'm not fussy about that is because it kind of makes it look like he's taking the moment of an acceleration and not the moment of an inertial force. So anyway, this is my particular preference. I like to visualize the inertial force. We've seen the inertial force with the steel block on the flimsy steel ruler. I'll show that again in class. Anyway, in the next movie, you will see how much of an advantage you can get if you take moments about an arbitrary point P. And usually the advantage is if there's a bunch of forces going through P and you take moments about P,